I'm Misha, Adobe creator and producer of the Deep Dive podcast. Welcome to Season 3, Episode 16, and today we will be doing a deep dive into why ice floats. Okay, it looks like Grace and David have their snacks ready and are settled in behind the microphones, so let's get going.
You know that moment, right?
Yeah.
You drop ice cubes in your drink and they just float.
Mm-hmm.
It's so normal we hardly even notice it. But did you ever stop and think, wait, why doesn't it sink?
Yeah, it feels like it should, maybe.
Exactly. It seems heavier than water somehow.
Huh.
Anyway, that simple question, it kicks off a really fascinating deep dive for us today into one of water's most, peculiar behaviors, why ice actually floats.
It really is one of those everyday things that points to some pretty deep science. We've been digging into some really good blog posts that break this down.
Right.
And our mission, essentially, is to unpack the science behind it all. We're talking density, sure, but also water's weird molecular structure, buoyancy, and actually why floating ice is so incredibly important.
It's not just about our drinks then. Okay, so density. Let's start there. We hear that word a lot, but what's a good way to think about what density really means?
Okay, imagine packing a suitcase.
Right.
Two identical ones.
Okay.
One, you cram absolutely full of, heavy textbooks. It's packed tight.
Right. Heavy.
That suitcase has high density. Lots of mass in that fixed volume. Now, the other one, maybe just a swimsuit and a towel. Very light stuff.
Barely anything in it.
Low density. So density is just, how much stuff, how much mass is squished into a certain amount of space.
Got it. Suitcase full of bricks versus one with a couple of feathers. Makes sense. And the rule is generally denser things sink in less dense things.
That's the basic idea, yeah. If something's denser than the liquid it's in, gravity pulls it down through the liquid. Less dense, it floats.
Swim enough.
But in the sources really hit this point, it's not just about how heavy something is overall. Think about a tiny pebble sinks straight away in water.
Yep.
But a huge, massive log floats.
Ah, right. Because even though the log weighs way more, its mass is spread out over a much bigger volume. So its density is lower than the water's. It's like being light for its size.
Exactly. Perfect way to put it. The pebble is like that dense suitcase lots packed in small. The log is like a giant suitcase, but filled with, packing peanuts. Lower overall density. Okay. And here's a little twist on that. Something that sinks in, say, regular tap water might actually float in something else.
Oh, like how people float really easily in the Dead Sea because it's so salty.
Precisely. All that dissolved salt makes the Dead Sea water much, much denser than fresh water. So your body, which might sink a bit in a lake, floats high up there. It really shows floating is relative to the liquid you're in.
Okay, that makes sense. But what about really big things made of really dense stuff? Like, how does a massive steel ship float? Steel is way denser than water.
Yeah, that one gets people every time. It comes back to that idea you mentioned, average density.
Average density, okay.
While the steel itself is very dense, the ship's hull encloses a huge amount of air.
Right, it's mostly empty space inside.
Exactly. So if you take the total the steel, the engines, the cargo, plus all that air inside, and divide it by the volume of the ship that's actually underwater, that average density ends up being less than the density of the water it's sitting in.
So the trapped air makes the whole thing effectively less dense overall.
Crucial for buoyancy.
Trade in your boring job for a brilliant career using Adobe Creative Cloud. Start learning now with the free trial link in the description.
And, thinking about our ice cube again, even those little trapped air bubbles you sometimes see inside, they contribute too, in a tiny way, lowering the ice cube's average density just a bit more.
Okay, density, average density, I think I've got that. But this is where water just, breaks the rules, isn't it? Because usually when stuff gets colder and freezes solid, it gets more dense, not less.
You've absolutely hit the key point. Most substances, their molecules pack closer together when they solidify. They contract. Water, it does the opposite. As it freezes at 0 degrees Celsius, it actually expands. It takes up more space.
Wow.
And it becomes less dense. That's the fundamental reason ice floats. It's being weird.
Water, the rebel. And apparently this is all down to something called hydrogen bonds and the specific way water molecules like to hang out together.
Yeah.
Can you break down that molecular dance for us?
Let's try. So a water molecule is H0, right? 1 oxygen, 2 hydrogens.
Yeah.
Now, oxygen is kind of greedy with electrons. It pulls the shared electrons in those bonds towards itself. This gives the oxygen atom a slight negative charge and leaves the hydrogen atoms with slight positive charges. So the whole molecule is polar, It has slightly charged ends, like tiny, weak magnets.
Tiny magnets. I like that. Easy to picture.
Yeah. And these slightly charged ends mean water molecules are attracted to each other. The positive hydrogen of one molecule is attracted to the negative oxygen of a nearby molecule.
Ah,
That attraction is called a hydrogen bond. It's not super strong, like the bonds holding the H and O together in the molecule, but it's strong enough to influence how water behaves in a big way.
so in liquid water, these little magnetic attractions, these hydrogen bonds, are just constantly forming and breaking as the molecules jiggle around.
Exactly. There's enough energy for the molecules to move past each other, break bonds, form new ones. It's very dynamic, a bit disordered. On average, each water molecule is loosely connected to about maybe 3.4 others at any instant. They can actually snuggle up quite close in this liquid jumble.
Okay, like a crowded room, people milling about.
Yeah, good analogy. But when water starts to freeze, when it loses energy, the molecules slow right down. And those hydrogen bonds become more stable. They lock the molecules into a very specific, very orderly 3D arrangement, a crystal structure.
Like lining up for a formal dance instead of the mosh pit.
Huh. That's a perfect way to think about it. Yes. It forms a crystalline lattice, usually a hexagonal shape for common ice. And in this rigid structure, each water molecule forms stable hydrogen bonds with 4 neighbors. Not 3.4, but exactly 4.
4 specific dance partners in a set pattern. And somehow this orderly dance makes it take up more space. That seems backward.
It does feel counterintuitive, doesn't it?
Right.
But to make those 4 hydrogen bonds work properly in the right orientation, it's called a tetrahedral arrangement, the molecules are actually forced to be farther apart on average than they were in the liquid. This specific geometry creates this open, cage-like structure with, well, empty space built into it. You can see these hexagonal rings in snowflakes.
So the bonds, the very things pulling them together, end up creating a structure that holds them further apart overall in the solid state.
Precisely. The need to maintain that perfect, stable bonding arrangement overrides the tendency to just pack as closely as possible. The liquid mosh pit allows for closer crowding overall than the structured formation dance of ice. More space for the same number of dancers means lower density.
Wow. Okay. That molecular picture really explains the why. Now, the blog post we looked at, they put some actual numbers on this difference, didn't they? How much less dense is ice?
Yeah, the numbers really help. So for typical ice, the kind we usually encounter called ice, its density at 0 degrees Celsius is about 917 kilograms per cubic meter.
Okay, 917. And liquid water at that same temperature, 0 Celsius.
Liquid water at 0 Celsius is denser, around 999.8 kilograms per cubic meter.
Almost 1,000, so quite a gap.
It is. And interestingly, liquid water actually gets even a tiny bit denser as it warms up from 0 to 4 degrees Celsius, hitting its maximum density of pretty much exactly 1,000 kilograms per cubic meter at 4 degrees C.
So wait, it gets denser as it warms up from freezing. That's also weird.
Also weird. Most things just get less dense as they warm up. But between 0 and 4C, water molecules can pack slightly closer as some of that rigid ice-like structure breaks down before thermal expansion takes over above 4C.
Okay, water is just full of surprises. So comparing ice at 917 to water at its densest, around 1,000, ice is roughly, what, 8 or 9% less dense?
Trade in your boring job for a brilliant career using Adobe Creative Cloud. Start learning now with the free trial link in the description.
Exactly, about 8 to 9% less dense, and that corresponds directly to about a 9% increase in volume when water freezes.
Which is why water pipes can burst if they freeze solid in winter. That expansion force is huge.
It's incredibly powerful, yes. And that maximum density at 4 degrees C above freezing, that's not just a weird quirk either. It has massive implications for, say, lakes in winter.
Oh, right. The blogs mention this. Because the water that's coldest, near 0 degrees C, is actually less dense than the slightly warmer water below it. It floats on top. So the lake freezes from the surface down.
Precisely. And that layer of ice then acts like an insulating blanket, protecting the liquid water underneath from the freezing air temperatures.
Allowing fish and other things to survive down below.
Exactly. The densest water at 4 degrees C sinks to the bottom, creating a relatively stable, slightly warmer refuge for aquatic life. Many fish enter a state of low activity, kind of like hibernation down there.
Wow. If ice sank, like most solids,
Lakes and rivers would freeze solid from the bottom up in cold climates. It would be catastrophic for almost everything living in them.
that's incredible. Such a huge consequence from this one strange property. Okay, so we get why ice is less dense, that molecular structure. But how does being less dense actually make it float? That brings us to buoyancy and Archimedes, right?
That's the next piece of the puzzle, Archimedes' principle. A classic. It basically says that when you put an object into a fluid like water, the fluid pushes upwards on the object.
The buoyant force.
Yes, the buoyant force. And the strength of that upward push is equal to the weight of the fluid that the object has pushed out of the way or displaced.
Okay, so the water pushes back up based on how much water the ice shoves aside.
Exactly. Now, an object floats when that upward buoyant force perfectly balances the downward force of the object's own weight due to gravity.
Right, push up equals pull down.
And because ice is less dense than water, a certain weight of ice takes up more volume than the same weight of water.
Okay, yeah, 9% more volume.
So when you put an ice cube in water, it only needs to sink partially. It only needs to push aside a volume of water that weighs the same as the entire ice cube.
Because the water is denser, it doesn't need to displace its own full volume to equal its weight.
Precisely. It sinks just enough for the weight of the displaced water to equal its own total weight. The buoyant force matches gravity, and the rest of the ice cube stays happily floating above the surface.
That clicks. It makes perfect sense now why only part of it is submerged.
Yeah.
And the iceberg example is just this on a massive scale, right?
A perfect and often dramatic illustration. Icebergs are typically freshwater ice, density around 917 kilodrumina. Seawater is denser because of the salt, maybe 125 kilodrumina. So if you compare those densities, 917 divided by 1025, you get about 0.895. That tells you roughly 89.5%, or let's just say 90%, of the iceberg's mass and volume needs to be below the water surface to displace enough seawater to balance its weight.
Which is why only about 10% is visible above the water. The classic tip of the iceberg.
Exactly that. And because salt water is denser than fresh water, an iceberg actually floats slightly higher in the ocean than it would in a giant freshwater lake. It needs to submerge a bit less volume to get the same buoyant support.
Fascinating. So floating is this equilibrium state. Gravity pulling down, buoyancy pushing up, all determined by these density differences.
You got it. A balance of forces.
We've really gone deep into the how and why ice floats. But like we touched on with the lakes freezing, the sources we read made it really clear this isn't just, a neat science fact. The ecological importance is huge.
Oh, absolutely massive. It's fundamental to life as we know it in many parts of the world. We already mentioned the insulation aspect for lakes and rivers. That ice layer is literally a lifesaver, preventing complete freezing and providing that 4-degree C refuge.
Unbelievable impact right there.
Then there's climate regulation. Think about the vast sheets of sea ice in the Arctic and Antarctic. Ice is white, right? Highly reflective.
Yeah, reflects sunlight.
Exactly. It has a high albedo. It bounces a lot of incoming solar energy back into space, which helps keep the polar regions cool, and that in turn helps regulate the entire planet's temperature.
Whereas dark ocean water would just absorb that heat.
Absorbs much, much more. And this leads to a dangerous feedback loop we're seeing now with climate change. As temperatures rise, ice melts, exposing more dark ocean, which absorbs more heat, which melts more ice.
The ice albedo feedback, yeah, that's worrying. Accelerating the warming.
It is. And another huge piece is ocean circulation.
How does floating ice affect currents?
Well, when seawater freezes, something interesting happens. The salt gets largely excluded from the ice crystal structure. It doesn't fit well.
So the ice is mostly freshwater.
Mostly, yeah. And the salt gets left behind in the unfrozen water nearby, making that water extra salty and therefore denser. And because it's also very cold, this cold, dense, salty water sinks.
It sinks down deep.
Right down. This sinking, primarily in the North Atlantic and near Antarctica, acts like a giant pump. It drives the massive global network of deep ocean currents called the thermohaline circulation, or the ocean conveyor belt.
And that conveyor belt moves heat around the planet.
Moves heat, salt, nutrients. It's absolutely critical for global climate patterns and marine ecosystems, and it's partly driven by the process of sea ice forming and floating.
Wow. Okay. Insulation, climate control, driving ocean currents. What else?
Well, the ice itself is a habitat. Sea ice is a crucial platform for animals like polar bears, seals, walruses, penguins. They use it for resting, hunting, breeding.
Right, like solid ground in the middle of the ocean for them.
Exactly. And it's not just on the ice. The underside of sea ice is a whole ecosystem, too.
Yeah.
Algae grow there, clinging to the bottom surface.
Really? Under the ice?
Yep. And when the ice melts, especially in spring and summer, it releases these algae, along with nutrients that were trapped in the ice, into the water column. This fuels huge blooms of phytoplankton, tiny marine plants,
Which are the bottom of the food chain.
the very base of the marine food web in polar regions. So, the cycle of ice freezing, floating, and melting directly supports this vast explosion of life every year.
It's staggering. To think that this thing we barely notice, an ice cube floating in a drink, is tied to survival in lakes, global climate, ocean currents, and the entire foundation of polar food webs.
It really is profound when you unpack it. So just to recap, ice floats because water molecules, thanks to hydrogen bonds, arrange themselves into an open, crystalline structure when they freeze.
Making solid ice less dense than liquid water.
About 9% less dense. And Archimedes' principle tells us that because it's less dense, it only needs to displace a portion of its volume in water to achieve buoyancy, to get that upward force balancing its weight.
And this simple fact is critical. It insulates lakes, reflects sunlight to cool the planet, drives ocean currents through salt rejection, and provides a literal platform and food source for life in the polar regions.
Couldn't have said it better myself. It's a chain reaction of consequences stemming from those tiny water molecules and their hydrogen bonds.
So, yeah, the next time you see ice floating, maybe give it a little nod of appreciation.
Definitely worth doing.
And maybe take a moment to think about that incredible balance, how these unique properties of water work together, and how vulnerable that balance might be. Makes you wonder about water's other strange properties too, doesn't it? What other vital roles are they playing?
Absolutely. Lots more to explore there.
Absolutely.
Thanks for joining us for this deep dive.
It's been a pleasure.
We'll see you next time.
See you later.
And that's a wrap on this deep dive. I'm Misha, and let me send out a huge thank you for listening. If you want more content on gaming, education, or other fun stuff, head over and find me on YouTube. Link is in the show notes. Thanks again for tuning in, and I'll catch you on the next deep dive.